All right, so I don't know that I want you to do these. These are, I'll show you the answers to these because these are very similar to what we've had in the homework and the ones that, that we just did. But let me just march through them. 32 is 2 to the 5th, and we rationalize 1 over the square root of 2 to be square root of 2 over 2. And you get 4 plus 1/2 is 9/2. And then on the second one, we rationalize the first, and then we get those two expressions. We make a common denominator with the second term, and then we can we get to this thing combined. Okay, so did everybody follow that? Did that go too fast? So step by step, first rationalize this, and then to add these two together, we make a common denominator by multiplying the second one by 5x over 5x. And then we can add the 5x to the 2, and we have 2 plus 5x times the square root of 5x. All right, so let's now talk about multiplying radicals. And we're going to talk about multiplying them and also dividing them ultimately. So here we were, just up until now we've been adding radicals. And in order to add radicals, they needed to be similar, right? You can add 3 root 2 to root 2 and get 4 root 2. With multiplying, you don't need similar radicals. Radicals multiply regardless of the of what's inside the radical. What's important, though, is that the index of the radical stay the same. So if we have the square root of 5 times the square root of 2, we get the square root of 10. And this goes back to the principle of applying powers to separate variables. Just imagine if this was n was 1/2, we would have a to the 1/2, b to the 1/2, and so connecting it to the example, that would be like having 5 to the 1/2 times 2 to the 1/2 would be the same thing as taking 5 times 2 to the 1/2. Okay, so sometimes you get radicals and the radicals will disappear, not because either of these will simplify. Square root of 2 doesn't simplify. 50 simplifies into 5 radical 2. But when you multiply these two together, you get something that's a perfect square, and you get 10. So we're going to rely actually on this. When we get to division, we're going to find that we'll be able to eliminate some radicals by choosing what we're multiplying in order to make these nice perfect squares that we can take the square root of. Now, multiplication works just the same as it works with anything else. The distributive property holds, so if we have 3 times the expression 2 plus square root of 3, we distribute the 3 and we get 6 plus 3 square root of 3. Hopefully no surprise there. A radical is just a number, so we can do that as well. The square root of 3 you multiply that times 5, and then you multiply it by the square root of 3. And so when you do that, you have opportunities for simplification, and in this case you take the square root of 3 times the square root of 3 to get the square root of 9, and you end up with 3 once you simplify it. So the one thing that doesn't work is that you can't multiply radicals that have different indices. These have to be the same index, so that means you can only multiply the cube root of 3 times the cube root of 3 of something, or the square root of something times the square root of something else. If you have something like the square root times the 5th root, there's no real way to simplify that. Now, one of the methods that we've used in multiplying before is we've used FOIL, the first outside, inside, last, and that works when you have these binomial expressions in radicals as well. You just do exactly the same thing that you did whether you have just ordinary variables or numbers with exponents. We multiply the first and the outside to get square root of 3 times 2 times the square root of 3 minus square root of 3 times negative 1. And then the inside and the last give you 2 more terms. And so when we simplify them, notice what happens is once we simplify them, we get a binomial form again. So this frequently happens when we have the same radical in each of the binomial expressions, because what happens then is that when you're multiplying, the square root of 3 times the square root of 3, the square roots go away. And so the only ones that you're accumulating are when the square root of 3 multiplies by one of the non-radicals. So it works exactly the way you would expect. When you have two different binomials, just multiply all terms out. It's possible that you end up with 4 terms that you can't simplify. It's possible that you end up with 3 terms. It's possible you end up with 2 terms, and you'll see that it's possible that you end up with only 1 term. So unlike when we're taking linear binomials like x plus 1 times x minus 2, you generally get 3 terms. Here you can get anywhere from 1 to 4 terms. Okay, another example. If we take the square root of 3 times, or plus 2 times the square root of 3 minus 2, so we'll do that by FOILing. So square root of 3 times the square root of 3 times negative 2 times the square root of 3 plus the square root, or plus 2 times the square root of 3, and we get 2 times negative 2 is negative 4. And so when we simplify that, the terms here, this negative 2 times the square root of 3, notice that the signs are opposite on these two. And so the square root of 3 times the square root of 3 gives us 4, and we just get this whole thing as negative 1. Notice the pattern here. This is a lot like we had when we had x plus 1 times x minus 1, where we would have x squared minus 1. It would be the difference between two squares. Well, when we have radicals in there and we take something like this, and we call this the conjugate. Square root of 3 plus 2 is the conjugate of the square root of 3 minus 2. Square root of 3 minus 2 is the conjugate of square root of 3 plus 2. When you multiply conjugates, you get the difference between the two terms squared. So if they're radicals, or if they're the square root, then all the square roots disappear on you and you get a single number. Now this happens even if you have two different square roots. So if we look at this one, the square root of 5 plus the square root of 2 times the square root of 5 minus the square root of 2, you look at all those factors you get, and you notice that the first one turns out to be 5, and then we have plus and minus the square root of 10 and minus 2. So this whole mess turns out to be the difference between 5 squared and 2 squared. Ultimately is 3. Okay, so a few for you to try. Okay, so 22. Good, okay. So I was talking about this notion of conjugates. And so let's look at each of these and see if we can come up with a conjugate here. Okay, so the conjugate of the square root of 7 plus 3 is minus 3, right? And the conjugate of this next one? Plus, right. And then the conjugate of the second one has the negative sign in front of it. So when you multiply these out, okay, I did it every term. I FOILed these. What I really get is if you just take the first and the last terms squared, you know that the middle terms cancel out. So what would have been fine here is to say this is 7 minus 9, because that's square root of 7 squared is 7. Minus 9 gives you negative 2. Same thing here. We can say this is going to be 6 minus 2 is 4. And here we have 25 minus 3 square root of x squared, which makes 9x. And so we get that. All right, so what good's a conjugate? if we have radicals in the denominator, but it's not just a radical, it's the sum of two terms, either two different radicals or a radical and an integer or a radical and a variable or any combination like that. If we did this by just rationalizing like we did before, where we would choose the square root of 2 over the square root of 2, what would happen is you'd have the square root of 2 in the numerator, and then in the denominator you'd have 2 plus the square root of 2. So you didn't eliminate a square root by multiplying it by just the square root of 2. So what we've seen before is that when you multiply by a conjugate, you get rid of the radical. And so basically your rationalizing factor then is going to be the conjugate of the denominator. All right, so in this case, the numerator stays square root of 2 minus 1, because it's just square root of 2 minus 1 times 1. And then this is going to be the square root of 2 squared minus 1. And so when we calculate this out, we get square root of 2 minus 1. Now, isn't that interesting? At least I find it's interesting. If I take the reciprocal of this, I get the conjugate. Okay? It's not always the case, but there's always some relationship between the conjugate and the reciprocal of its pair. We'll see these in the next few examples. Okay, so with this one, we're going to choose the conjugate of 2 minus the square root of 3, which is 2 plus the square root of 3. And we simplify it further. We get 2 squared minus 3 is 1, and so we don't have to write the 1. We can write it like that. So if you factor out the 4 we had here, okay, if you factor out this 4, what you have inside is 2 plus the square root of 3. All right, so this is still proportional to the conjugate, and you would expect that because you're multiplying it by the conjugate, and this eliminates the conjugate. But you don't know what this product is going to be. It just happened in this case to be 1, and the case above us was 1, and so that's why, you know, it turned out nicely to just be the reciprocal. When it doesn't equal 1, then you get something proportional to it, but it's still in the some factor times its conjugate. Okay, so we look at this one. 6 over the square root of 1 plus 1. And there's its conjugate. And so square root of 7 squared is 7. 1 squared is 1. And so we get 6 times the square root of 7 minus 6 over 6. Now, as it turns out, I probably multiplied this thing prematurely, because if I just kept this in parentheses, I would not have to undo what I've just done. I get 6 over 6, and so I get square root of 7 minus 1. So here's a case where this 6 in the numerator just kind of went away, and we just get the conjugate in the as the solution. Okay, and then one last one here. We got 5 over 9 minus the square root of 6. And there's its conjugate. Multiply this thing out, and so we get 9 squared minus 6. Now here, I didn't multiply this 5 on through, but now I can see that this 5 and the 75 can be reduced, and I'll get 9 plus square root of 6 over 15. All right? Everybody follow all the examples? I'll give you a minute to catch up on your notes. All right, so, of course, time for you to try a few. Okay, how about that first one? What does that turn into? Anybody get an answer? Yes, Megan.
-2 plus root 5.
-2 plus root 5, okay. Okay, everybody get that? Now, I changed the order of that, but -2 plus square root of 5 is exactly the same thing. There's no preferred order. So, when you have a -1, simplify out the denominator just by changing the signs of the numerator, okay? That'll give us a simpler expression. Now, the next one, very similar to the one that we had on the page before. What'd you get there? Anybody? Lauren, what'd you get?
9 minus the square root of, square root of 6 over 15.
Okay, great. I think that's, oops, too much on that one, but, okay, 9 minus the square root of 6 over 15. And the last one, we have a bunch of radicals going on here, so we take the conjugate of the denominator, and so we multiply like this, and then simplify, and we're done with our answer there. Oops, that's not what I wanted. Okay, I'd like to make a comment about what we're doing here. This looks like we're just simplifying ratios, right? But in fact, what we're doing is we're doing division. All right, so if I look at the first one, if I rewrite that, I can write it like this, right? And so what we've, in essence, have been doing is division by, okay, 2 more of these. So, Ivan, will you put the first one on the board, and Sierra, will you put the second one on the board?
Sure.
So you see how we ended up with 4 terms in the numerator, and then that 3 minus 4 in the denominator is -1. So just as a matter of simplifying, I just changed all the signs in front of all the radicals from negative to positive and positive to negative. So all those markers work. And then we get 4 terms. And that's typical when you have something like this where you have nothing matches up here. So you're going to expect that you're going to get 4 terms. Sometimes I'm not so sure. Okay. Everybody okay with that? So watch those conjugates, when you have one square root and one that's not a square root, make sure that that you're treating those properly, that it's either the number squared, or if it's a square root, then it's just the square root sign gets removed. All right, so now we're going to go into 7.5, and 7.5 has to do with radical equations. So now that we know how to handle radicals, let's put it in an equation. So how do you solve these? And we're going to solve these using the principle that if 2 things are equal, then we can bring both sides to the nth power, that will be equal as well, okay? So in this case, of course, when we're using radicals, we're going to have n be a fractional number. So if we're going to take something like, if u has, let's say, a radical in it, like square root of 2, or v has a square root of 2, then we can square both sides and we get rid of that square root. So in the simplest case, if we just have square root of x minus 4 equals 0, what we do is we work these very similarly to the way you work absolute values. Okay, so what we did there was we isolate, in that case, the absolute value, but in this case, the radical, and then we square both sides. And so then the left side just becomes x, and the right side equals 16. Now, with these, just like with absolute values, it's important that we check. So if x equals 16, I'll insert x into the, or I'll insert 16 where the x was, and so I get 4 minus 4 is 0, and so it works out. So let me run through a few examples, and then I'll have you do a few of them. So we can have an expression inside the square root, like if it's just the square root of x plus 1. The radical is isolated, and then we're going to bring that, we're going to square both sides. And so we get x plus 1 equals 4. Subtract 1 from both sides, and we get x equals 3. And then from here, I'm going to check. I'll stick my 3 where the x is. 3 plus 1, take the square root of that, and I get 2 equals 2. No problem. Okay, so let's say we have this equation. First step always is to isolate the square root. And then we're going to square both sides. I get 9 minus x equals 7 squared, or 49. And then I'm going to subtract 9 from both sides, and I get negative x equals 40, and x equals negative 40. Okay, negative 40. What I'm going to do with that is I'm going to stick it in the original equation, and I get 9 minus negative 40 minus 8 equals negative 1. And sure enough, I get square root of 49 minus 8, which is 7 minus 8 is negative 1. Okay, so that works. Try a third one. Here we have the square root of x plus 1 plus 2 equals 0. That doesn't look too different from that first one that I did. But when I isolate the radical and I square both sides, I get x equals 3. But now when I check, I get square root of 4 plus 2 equals 0, where 2 plus 2 does not equal 0. So this doesn't work. Every step that I took was proper according to the way that, that we're doing these things, but I'm getting a solution that doesn't work. Anybody know why? Where does this thing go wrong?
Like extraneous solutions?
Yeah, why do I get extraneous solutions out of this? That's exactly right. So first thing that happens here is that when I isolate the square root, I get a negative number. And so right there I know there's no solution to this. No real numbered solution to it. Okay? Does that make sense to everybody? Now you don't always have to spot that. If you spot it, you can stop here and say the square root's always 0 or more, so there's no solution. That's fine. Or if you work through the whole thing, you got to check, because if you check, you might get something that doesn't work. Okay, so time for you to do a few.